Okay, welcome back. In this video, we're going to take a look at sequences and limits in higher dimensions. And basically, this will be only a very slight generalization of what you know from the reals already. So this is section 12.3, sequences and limits. We'll start with defining a sequence, and again, this is basically what you know from the reals already. So, formal definition. A function f that is defined on the integers n including 0 to some higher dimensional r to the n is called a sequence in r to the n. And we'll also introduce a simpler notation with a k defined as f of k. Such a sequence is usually denoted as, well, that one is ready just as a k, and then the index k in the index set, and 0 in this case, or even more simple, a k and just the index set. And of course, we also have to define what it means if a sequence is convergent. So we'll do that as well. A sequence ak and 0 is called convergent if there exists a vector a in r to the n such that ak comes closer and closer to a. You remember in r we used the absolute value to measure the difference. We are now in r to the n, so we can't use the absolute value anymore, we just use the norm. Okay? So if there exists a vector a such that the norm of ak minus a, if that one tends to 0 as k goes to infinity. So basically, we look at the one-dimensional sequence of the norms of ak minus a, and then say if this tends to 0, then ak converges to a. And as in dimension 1, the vector a is then called the limit of that sequence. Vector a is called the limit of the sequence ak and denoted by a equals lim ak. Okay, you know all that notation from one dimensions already. And it becomes even simpler. That's a little lemma there. One can show that basically sequence convergence in higher dimensions simply means each of the coordinates converge. Okay, so basically instead of regarding a sequence in higher dimensions, we can just resort to having a look at the single coordinates, regard those as real sequences, and then investigate if these converge or not. Okay, so let AK and 0 be a sequence in Rn, and let A be in Rn with, now we need to introduce a notation. So this AK is a vector that consists of n coordinates, and we just denote this as alpha 1 k to alpha n k, and A will denote this as alpha 1 to alpha n. And then the sequence is convergent if and only if the coordinate sequences also converge. Then AK and 0 is convergent with limit A if and only if for each I from 1 to n the following holds. And I must hold that the sequence of the alpha I k for the index at k at fixed I, this sequence is convergent. And second, the limit must be correct. So the limit of this alpha I k sequence over k is alpha I. Okay, or in simpler words, a vector value sequence converges if and only if each coordinate sequence converges as a sequence in R. Okay, so a little less formal. A vector valued sequence converges if and only if each coordinate converges as a sequence in R. Okay, so sequence convergence just carries over to higher dimensions very simply. There's two more things that we need to define. First is a sequence can also be called bounded, and that's also very easy. It's bounded if the set of all of its elements is a bounded set. And then we're going to introduce the notion of a subsequence. We can also do this in R, of course, but we basically didn't need it much there. So we're only going to introduce that now. And that basically means you just pick a few of the points in the sequence in increasing order of the index. And whichever subset you pick here constitutes a subsequence. Okay, so formally, let's define that. First part of the definition. A sequence is called bounded simply if the set of all AK k in N0 is bounded. And second, let AK and 0 be a sequence. And let F be a function that maps the integers to the integers, and that is strictly increasing. And by that I mean for two integers p and q, where p is greater than q, we also get f of p is greater than f of q. So we don't jump back in the index set. That's the idea. Okay. And then we define a new sequence. Then a sequence, we call that AK prime. Defined as AK prime equals AF of K. That sequence is called a subsequence of AK. And finally, the limit of a convergent subsequence of any sequence is called an accumulation point of the original sequence. The limit of a convergent subsequence of some sequence AK is called accumulation point. Of that sequence AK. Okay, before we go on, let's see a few examples here. First one. Let's define our sequence AK as follows. AK is defined as -1 to the k, and then square root of 1 minus 1 over k plus 1. And the second coordinate is 1 minus 1 over k plus 1. So that's a two-dimensional function. First note that this second part here, note that 1 minus 1 over k plus 1, that of course converges, and it converges to 1 as k goes to infinity. Okay, so this second part here, that converges to 1. This part here would also converge to 1, but then we still have this -1 to the k. So the sequence itself does not converge, yeah? As the first coordinate gets closer to 1, -1, and then jumps between those two. Okay, so AK does not converge. However, it does have convergent subsequences. However, it has convergent subsequences. Namely, let's define those. First subsequence that we look at is AK prime. AK prime and 0. We'll simply define this as only taking the even indices. And we'll write this in a very simple way. We'll write this as a 2k k in n0. So that means we use the original sequence A, and we only take all indices of the form 2k for some k in n0. So only the even the even indices. Okay, so that means what we get here is minus 1 to the 2k, square root of 1 minus 1 over 2k plus 1, and 1 minus 1 over 2k plus 1. And now, of course, you can easily see that this here, minus 1 to the 2k, that is exactly equal to 1. This latter part here still goes to 1, and this also goes to 1. So that means this whole sequence here converges to the point 1, 1. Okay? So there is one convergent subsequence that converges to the point 1, 1. And of course, we could also easily define another subsequence that consists of just the odd indices of the original sequence A. So a 2k plus 1, k in n0. And that is minus 1 to the 2k plus 1, square root of 1 minus 1 over 2k plus 1, so 2k plus 2, and 1 minus 1 over 2k plus 2. And now this first part, this minus 1 to the 2k plus 1, this is equal to minus 1 for any k. And again, these latter parts here, those converge to 1. So what we get now is again a convergent subsequence, but this time it converges to minus 1, 1. Okay? So this sequence has two accumulation points, 1, 1 and minus 1, 1. So 1, 1 and minus 1, 1 are both accumulation points of the sequence AK. Okay, we'll have one more simple example for a multi-dimensional sequence. Example 2. This time we'll define the sequence recursively. And we call the elements F and G. So that'll be the sequence F, K, G, K. And we start at 1 this time. We'll define this recursively. So just that you see this is also possible. Through the following recursion, we'll start at F1, G1, 1, 0. And then we'll define Fk plus 1 and Gk plus 1 through the first will be the sum of Fk and Gk, and the second will just be Fk. Okay, and if you want, you can also write this conveniently in matrix vector form. So you can just say this is a matrix multiplied with the vector fkgk, and the matrix would then have to be 1, 1, and 1, 0. Looks that way. Okay. Now, if you look a little closer, then what you get here is basically the following. The gk is the same thing as fk minus 1. There's always lags behind by 1. So that means fk plus 1 is fk plus gk, and gk lags behind by 1, so gk is fk minus 1. So basically this is a complicated way of formulating this recursion. Fk plus 1 equals fk plus fk minus 1. And this sequence is known as the Fibonacci sequence. It starts as 0, 1, and then the next part in the sequence is always the latter two parts summed up. So starting with 0, 1, 0, 1. Then we sum up those two. 0 plus 1 is 1. Then we sum up the last two. This is 1 and 1. So the next element of the sequence is 2. Then we sum up 1 and 2, that is 3. Then we sum up 2 and 3, that is 5. Then 3 and 5, that is 8. Then 5 and 8, this is 13. And you can see the sequence is now starting to grow more and more rapidly. So this is an unbounded sequence, and of course it does not converge, it goes to infinity. Okay, so this f is the Fibonacci sequence, and this two-dimensional version is just a complicated way of writing it down. However, that complicated way is useful, and we'll learn in the exercise classes why that is. Okay, enough examples here. We conclude by one more theorem. And that's theorem on sequence convergence, that is known as the Bolzano-Weierstrass theorem. Of course, that one also holds for sequences in the reals only. We just didn't formulate it that way back then. What it says is simply each bounded sequence has at least one accumulation point. So for each bounded sequence, there is some subsequence that converges. And as a simple corollary from that, we can also conclude that if a set X is compact, so means it is bounded and closed, and there is a sequence in that set, then this one has a convergent subsequence. And as the set X is closed, the limit of that sequence will be in X. So the subsequence converges in the set. And that's something that we'll have to make use of sometimes. Okay, let's write that one down. Each bounded sequence has at least one convergent subsequence, meaning at least one accumulation point. In particular, if X is a compact set, and a K is a sequence in X, then AK has a convergence subsequence with limit in X. So the limit cannot lie outside of X. It needs to be in the set X itself. Yeah, what we're using here basically is the fact that X is closed. So compact means closed and bounded. So that here is because X is closed. And the fact that there is a convergence subsequence, that is due to the fact that X is bounded, and that theorem of Bolzano and Weierstrass. Okay, so much about sequences, accumulation points, and subsequences. Next thing we'll do is we'll apply this to functions so that we can define function limits and then define continuity in higher dimensions.